Okay, so today's lesson, as you can tell, we're going to be talking about a whole new set of numbers called the complex numbers. And I just want to use this slide that you're looking at here as a way to kind of introduce the need for today's lesson. Years ago when I taught, it's been a long time ago, when I taught Algebra 1, we would occasionally run into situations like this, solving an equation like you're looking at on the board. So we would begin the normal process of trying to isolate x. So the first move would be to subtract 25 from both sides. Then we were taught to undo raising something to the second power by doing the square root. And that was done on both sides. And because it's a quadratic, if you do the square root on both sides, we always have to include plus minus because the number plugged in for x could be positive. When you square a positive number, you get a positive result. When you square a negative number, you get a positive result. So the solution for a quadratic is typically two different numbers. In this case, a positive number and a negative. Well, we got down to this point and we said, there is a big problem. Because this is telling me in the real number system to take some number, multiply by itself, and get negative 25. Well, that's not possible. You can't multiply a number by itself and end up with a negative result. Two positives would be a positive. Two negatives would be a positive. So when we got to this point in Algebra 1, we just said, not possible, and we stopped. Well, today, it's going to be possible, because we're going to open up for you a whole new set of numbers that are not part of the reals. These are called the set of complex numbers, and they're going to utilize this new number that we're going to talk about, the number I. The number I, if you want to think of this as a definition or just a truth, the number I is literally equal to the square root of negative 1. From that statement, we can come up with another truth. Just think about using some algebra. If I wanted to remove the radical by raising both sides of this equation to the second power, then I get another true statement, which is here. I squared is equal to negative 1. So those two statements, those two little equations are going to be used a lot in this lesson and in other lessons down the road. So I just am showing you here some numbers that we call pure imaginary numbers. And it's going to be the goal of this lesson to show you how that the square root of negative 49 is actually 7i. The opposite of the square root of negative 25 is negative 5i. And the square root of negative 7 is written as I times the square root of 7. So that's kind of a preview of where we're going. So let's jump right in with some examples. Okay, so let's look at some problems like what you're going to be doing in your homework, and this involves finding the square roots of negative numbers. I'm going to show the red radical as the factoring of two blue radicals. Factoring means just showing this same expression using multiplication. So I'm going to show it as the square root of negative 1 times the square root of 36. Now, I'm not saying you have to do this every time. I'm just trying to do this to introduce this concept of using the number I. Because on the previous slide and in your notes, I told you that the square root of negative 1 literally is I. And we know what the square root of 36 is. So I put this together, and my final answer for letter A is going to be 6i. Letter B, I'm going to show the same factoring. Let's do it as the factoring of the square root of negative 1 times the square root of 64. The product of these two blue radicals would equal the red. Well, let's simplify, because we now know that the square root of negative 1 is I, the square root of 64. So we put it together, and the answer to this radical would be 8I. Now letter C is a little different than A and B, because I hope you recognize that 24 does not have a perfect square root like the other two did. So we're going to have to do a quick refresher in how to simplify radicals. I know you covered this in Algebra 1. Well, we know the number I is going to be needed to make the negative 24. And so the way I think about this, you may have your own method, but the way I go about this is I'm trying to find a perfect square root factor of 24. Another way of saying that is a number that has a perfect square root that divides evenly into 24. And I hope you remember that, or recognize that that would be the square root of 4. Well, the square root of 4 times what would give me 24? All right? So the goal of this, since I cannot remove the entire number from the radical like I was able to in letters A and B, I'm going to remove as much as I can from the radical using the square root of 4, which is 2, the square root of negative 1, which is I, and we still have 6 under the radical because there is no perfect square root factor of 6. 6 itself obviously does not have a perfect square root, so this ends up being our final simplified answer. Any questions so far? Okay. Let's try letter D. Using that same factoring technique, I'm going to use the square root of negative 1 to come up with the negative. And I'm going to choose the biggest square root factor of 32 that I can find, and that just happens to be the square root of 16. 16 goes evenly into 32, and it has a perfect square root. To make positive 32, I'm going to have to multiply by the square root of 2. And now I'm ready to write the imaginary number answer. Square root of 16 is 4. Square root of negative 1 is I, and then we're going to show that being multiplied by this radical that cannot be simplified, the square root of 2. Good. All right. Same thing on the square root of negative 18. I'm going to start off with the square root of negative 1. I'm thinking of a perfect square root factor of 18, and that would be 9, the square root of 9, times the square root of 2. All three blue radicals multiplied together should equal the red. That's what factoring is all about, rewriting an expression using multiplication. The square root of 9 is 3. Square root of negative 1 is I times this radical that cannot be simplified. All right, so let me just stop for a second and see if you have any questions on how to simplify the square root of negative numbers using the number I. Any questions? Great. All right, let's do another example. Now we're going to include some multiplication. I want you to think of I as a variable, even though it's really not. Technically, a variable is a letter that stands for any number. Well, I doesn't just stand for any number. It always represents the square root of negative 1. But when it comes to multiplication, you can think of it as a variable when you're thinking about your exponent rules. For example, if I multiply these together, I'm first going to multiply the coefficients. 3 times 4 is 12. If I multiply I times I, remember in your exponent rules, these are called like bases. And each of these i's has an invisible 1 exponent. So if you're multiplying like bases, you were taught to add the exponents together, and this would produce I squared. Okay, big statement I'm about to make right now, and a lot of people miss points on tests and quizzes because they stop at this point. But we identified at the very beginning of this lesson that I squared is actually equal to a number. Do you remember that? Go back to the very beginning. -1? Okay, so when you see I squared like this, you need to immediately replace it, or at least mentally replace it, with -1. You should never leave an answer as I squared or having I squared in it, because I squared is literally the number -1, so the simplified answer here is going to be -12. No, I squared is just -1.
Oh, okay.
Got it?
Yeah.
Okay, good. Okay, let's work on letter B. According to PEMDAS, I would do powers or exponents before I would do multiplication. So I'm first going to take care of squaring -7i. And that becomes positive 49i squared. Now I can multiply the coefficients together. That's 2 times 49. It's 98. I to the first times I to the second. You just add those exponents together and you get I to the third. Well, let's think of I to the third for just a minute, because we didn't give you a technical answer for I to the third yet. We're going to talk about that in just a minute. But we do know what I squared is, right? I squared is what number? Okay, so let's just think of I cubed for a minute as I squared times I. And you said I squared is -1. And so what's -1 times I? What's -1 times x? -1x, or just -x. What's -1 times I? -I, or if you want to think of it as -1i. We don't really need to show multiplying by -1. So when you put these together, I to the third is really just -I. So it's almost like saying we're multiplying 98 times -1i, if you have to think about the -1 to help you out. So when we multiply those together, what do we get? What's 98 times -1? There you go. Any questions there? How many of you worked ahead and you got that right? Good job. Any questions on how we got -98i? Questions about why I to the third is -I? Okay, let's try letter C. We have 3 coefficients to multiply together first. So -3 times -5, positive 15. Positive 15 times 2 is 30. When you multiply these 3 i's together, you get I to the third. But we saw earlier that I to the third could be simplified as -I. So really, this is like saying 30 times -I. Final answer? -30i. Matthew.
Why would it be 30? Because since I actually represents something and it's -30 times -1, that would be I squared is -1. Okay.
Does that help?
Yeah.
You got it? Yeah. Anybody else have a question? Am I losing anybody? Stop me if I am. We're just going to keep building. Okay. Well, let's talk about some larger powers of I. We're going to work over here on the right for just a minute, and then we're going to come back and use what we've learned to answer D and E. Okay, so let's just work down my little list. I've gotten it started. Obviously, anything to the first power is just the base. In this case, I to the first is just I. We already learned that I squared is -1. We just learned that I to the third is what? Okay, I'm just going to show it as negative I. And if I go to I to the fourth, well, that's like saying I squared times I squared. Well, what's I squared? Well, what's negative 1 times negative 1? Negative 1 times negative 1. 1. Okay? So can you see what I'm doing here? I'm taking the blue and I'm writing it using two reds that we've already defined. Yeah, because negative 1, I'm literally saying this. Negative 1 times negative 1. Because that's what I squared is. Okay, let's talk about the next one. I took I to the fifth. You notice I'm just going up by one exponent each time. And I'm going to write it as I to the fourth, which we just defined, times I. Well, that's like saying 1 times I. What's 1 times I? 1I, or just I. Don't need the 1. Okay, let's think of I to the sixth. Well, what if we thought of it as I to the fourth, which is 1, times I squared, which is negative 1. Well, what's 1 times negative 1? Negative 1. You follow me? Let's take I to the seventh, and we'll think of that as I to the fourth times I to the third. Well, what's I to the fourth? 1. What's I to the third? You multiply those together and you get negative 1I, or just negative I. Okay, don't get too far ahead of me. I to the eighth. Let's do that as I to the fourth times I to the fourth. It's like 1 times 1, which is 1. So Dalton stole my thunder. Do you see the pattern? Do you see what's about to happen? We went I to the first, second, third, fourth, and then what happens with I to the fifth? It's just like I to the first. What about I to the sixth? It's just like I to the second. You can, or you can, as long as you know these four, if you want to, for example, I to the first should be the same as I to the fifth, because I just add 4 to that exponent. So every fourth exponent, if you just add 4, you're going to get the same result. I to the first and I to the fifth should be the same as I to the 5 plus 4. 9th, which should be the same as I to the 9 plus 4. 13th, which should be the same as I to the 17th, which should be the same as I to the 21st. Do you see what we're doing? Okay. I to the third should be the same as I to the seventh. 3 plus 4, which is the same as I to the 11th, which is the same as I to the 15th. You get me? All right? So that really helps when we go to problems like this. Okay, so I'm going to give you about 30 seconds, and I want to see if you can give me your answers to D and E. Okay, so tell me, Sam, what did you get for letter D? -1. Who got it? Tell me, Sam, how did you get it? Because there's more than one way. How did you come up with -1? So you started with I to the 6th, and you just added 4 and 4, because I to the 6th should be the same as I to the 10th, which should be the same as I to the 14th. How many of you did? Who did that? Okay, how many of you got it a different way? Matthew, what'd you do?
I subtracted 4 from each, so I got 14 minus 4 is 10, minus 4 is 6.
Which is kind of backwards of what we just said. All right, who else? You have a different way. Yeah. Okay, you did I to the 8th and I to the 6th, put them together. Fine. Anybody else? Okay. Let me see. Riley, what'd you get for I to the 23rd? -I. Who got that right? Okay. So any questions? I don't want to dwell on this, but I really wanted you to see this pattern. And if you understand this pattern, it really unlocks the ability to do these higher exponent versions of I. All right, so let's move on. All right, we've talked about pure imaginary numbers. That's just a certain number. It could be I itself, or it's a number multiplied times I. Well, what we're about to talk about is using the number I, but these are called complex numbers. Complex numbers look like what I have written there at the top of the screen. It's a real number that's in the A spot, plus this, what we're used to seeing as a pure imaginary number in this spot. A and B are both real numbers. So I can't stress enough what I'm about to say. I hope you really listen well, because I get people that are a little angry with me on tests because they go through all of the parts of the problem correctly. They arrived at, let's just pretend there's some problem you don't even know about, but they arrive at 3i correctly, did everything right. They arrive at 4 correctly, nothing wrong there, but they show me a final answer like that, and I have to mark the problem wrong. It does, because I asked for a complex number, and if you give me this, you have not given me a complex number. Complex numbers look like this. Okay? So to make this correct, I need to turn it around and say 4 plus 3i. So please remember that on homework and tests. Yeah? Man, I'm glad you asked that question. And it has to do primarily with graphing. There is a complex number plane. Okay? And instead of a y-axis, we have an I-axis. So when you graph this, it's like graphing the ordered pair 4, 3. 4 on the x, 3 on what would be the y, but it's called the I. So if you switch them, it's like you've switched an ordered pair, which makes a big difference. Okay? Yeah.
So essentially the x and y axes have been renamed to I and complex numbers?
No, the x is still the same. It's the same for real or complex. It's just the y-axis has been renamed. So if you just think of the 3 like you would the y-coordinate in the old system. It's pretty easy to plot. I hope we get a chance to plot some complex numbers. Okay? So you got the form? Let's do some operations like adding and subtracting. This won't take long because you've already learned in Algebra 1 about adding and subtracting polynomials and the importance of combining like terms. Well, these are not technically polynomials, but the principle is still the same. All we're going to do is combine like terms. So the like terms are the real numbers, -2 and 1. I just add those together. -2 plus 1 is -1. And then I have these other like terms, which are the pure imaginary numbers, 5i minus 7i. That's -2i. And so there's my answer. Subtraction is the same idea, but you got to be careful. People miss subtraction because not only am I subtracting -1, but I'm also subtracting 2i. So you probably learned in Algebra 1 this idea of distributing -1. You might want to take this problem and rewrite it yourself like this. And now you'll be sure to make sure that you subtract both of these. Dalton, you have a question? Oh, that's okay. I've got people in mind I want to call on. Thank you. Okay, Zach, can you finish this off and combine like terms? Very good. 5 plus 4i. Now we're going to look at some examples of multiplying complex numbers, and hopefully from Algebra 1 you remember the FOIL method. You need to treat these as though you would multiplying two binomials together. So remember FOIL. I'll just spell it out in case maybe it's been a while since you've looked at FOIL. F stands for the first two terms multiplied together. So 2 times 4 is 8. The O stands for the outer terms multiplied together, so 2 times negative 6i is negative 12i. The I stands for the inside or the inner terms multiplied together. 3i times 4 is positive 12i. And then the L stands for multiplying the last terms together. 3i times negative 6i is negative 18i squared. But don't forget that I squared really is equivalent to negative 1. And so, let me get my toolbar back. Sorry about that, for that delay. Okay, here we go. Remember, I squared is negative 1, and so in place of I squared, I'm just going to literally put negative 1. And now when you multiply negative 18 times negative 1, it becomes plus 18. So I just wanted to show you that, negative 18 times negative 1. And then now, since you understand it, hopefully, we can just make this plus 18. So remember, anytime you have I squared in your expression, you need to replace it with negative 1. Okay, so hopefully you can tell that the inside and the outside terms are going to cancel each other. And we put these other terms, 8 and 18 together, just add them up, and our final answer becomes 26. So the big takeaway from problems like this, when you're multiplying complex numbers, go back to what you remember from Algebra 1 using the FOIL method and combine like terms. These outer and inner terms won't always cancel, but if they don't, you just combine them like you're hopefully used to doing. Alright, so let's talk about some dividing of complex numbers. So this first example involves division of what we would call a pure imaginary number. So to basically simplify this division, I'm going to multiply both the top and the bottom by the number I. Because what we're pretty much going to do, obviously we're just multiplying by 1. We're not going to change the value of this fraction. But I am going to simplify it so that it's in complex number form, and that's going to involve getting rid of basically the I number in the denominator. So let's just work on the denominator first. If I multiply 5i times I get 5i squared. Well, once again, I squared is negative 1, and 5 times negative 1 is just negative 5. Okay, so now let's work on the numerator, and this is the distributive property. So I'm going to multiply 4 times I, that's 4i, and plus, now I'm going to multiply I times I, that's I squared, but again, I squared is negative 1. So now I need to write this in a complex number form. Okay, remember a complex number looks like A plus B I. For fractions like this, I need to essentially divide negative 5 into each one of these. I'm going to break this up into 2 fractions. The first part of the fraction will be just the regular real number part. So let's think of negative 1 divided by negative 5, and that's positive 1/5. Now we'll do the BI part, 4i divided by negative 5, and that would give us negative 4i over 5. And now it's written in the proper form. 1/5 minus 4i over 5. Or you could write this as 4/5 I. That's the same thing. I typically just put the I in the numerator. Okay, so letter B is a little different, as you can see. This was just the pure imaginary number 5i. Well, this is a complex number being divided. The way we handle these complex numbers is by using what is known as the conjugate. And the easiest way to explain a conjugate, the conjugate of this denominator, which is what you're always going to use, whatever the denominator is, use the conjugate of that. And the conjugate of 1 minus I is 1 plus I. So it's just taking the same terms, the same complex number, you just change the sign. Okay, this is known as the conjugate of 1 minus I. And we're going to multiply by that both top and bottom of the fraction. Okay, so the top part, just think of FOIL. All right, first terms together, 2 times 1 is 2. The outside terms, 2 times I, that's 2I. The inside terms, I times 1, that's I. And then the last terms, I times I is I squared, but remember, I squared is -1. Okay, and the denominator, if we did FOIL, we would do the first together, that's 1. The outside terms would be I, but the negative I would be the result of the inside terms. You see that? And this always happens with conjugates. You're always going to cancel the product of the outside combined with the product of the inside. When you combine those terms, those two will cancel each other every time. So now let's just jump to the last and do -I times I. That's -I squared. It's like saying minus -1. Okay? -I squared is negative, and -1 is I squared. Okay? So let's just clean this up. In the numerator, combine like terms, 2 plus -1 is +1. 2I plus 1I is 3I. And in the denominator, we just get 2. So remember, this isn't technically the complex number form. When we have fractions like this, we're going to break this up into 2 parts. The real number part, which is 1/2, and then the imaginary part, which would be 3I over 2. Okay, and that leads us to our final example. And this is where really the reason why we're learning this is so that we can solve equations. That's the big picture where we're headed later in this chapter. So we looked at an example of this early on in this lesson, but let's just go ahead and do a couple more. Solving for x means my first step is to subtract 32 from both sides. My next step would be to divide by 4 on both sides. To solve for x, I need to do the square root of both sides. And don't forget, you probably covered this in Algebra 1, but anytime you are forced to do the square root of both sides, like we are here, you must include plus minus for the number that you're solving. All right, and so let's come up here and finish this off. The square root of x squared is just x. And now we're going to be forced to simplify the square root of a negative number, which is what we talked about early on in the lesson. So let me rewrite using factors. I'm not saying you have to do this, but I just want to make sure you understand how I got my final answer. Okay, so I know I'm going to need the square root of -1 as one of my radical factors. I'm going to use the square root of 4 and the square root of 2. All of this multiplied together is equal to the square root of -8. All right, so let's simplify. The square root of -1 is I, the square root of 4 is 2, so that's 2I, and then multiplied times this radical that could not simplify. So that becomes my answer for letter A. Letter B, we're going to subtract 14 first. Then we're going to divide by 2. Square root of both sides. Don't forget plus minus. And now we're going to simplify the square root of this negative number. Well, you can think of it as the square root of -1 times the square root of 7. And the square root of negative 1 is I times the square root of 7. That's the answer for letter B. All right, so that is your assignment, the page and those problems. If you have any questions about those, you can send me an email or come see me in academic support. Work hard on them, and we'll check them out next time.